Towards the cloud. Perfect. All right. So that should work. And with that, I will hand it over to you, Michael. I think you have screen sharing ability.
I do. So
Okay.
thank you. Hi, all of you, and some of you I see every week now. Um, I'm going to share my screen. So this is the topic I'm going to cover today. Hold on for a sec.
You just got quieter, Michael.
Yeah, I know. I'm fixing
Okay.
something. I'm fixing something. Okay, got it. Okay. So I want to focus on the rate of climate system change in this session. And in doing so, well, I will touch upon a couple of topics I know you've already visited in the course. So just to reinforce them. Well, let me start with the temperature and recording of temperature. The development of today's thermometers and temperature scales began in the early 18th century. A man named Daniel Fahrenheit produced a mercury thermometer. But global temperature taking, which allows for the determination of a global average, began about 1880. This is because before then, there were not a sufficient number of weather stations established to allow for a more comprehensive measurement of temperatures across the planet. So a question for you, based on what you've been studying so far, how did climate scientists discover climate parameters before direct instrument measurements? And I open that up to anybody. Just pop in. So let me say it again. How did climate scientists discover climate parameters before direct instrument measurements?
Using things like ice cores and soil samples.
Okay. Is there a name for that you've studied?
Proxies.
Proxies, exactly. Okay, so
And Michael, you keep coming in and out for your level of sound, just so you know.
okay, thank you very much. I will speak louder as I can. Okay. And so, yes, it's basically to get the temperatures before the 1880s, proxies were used, and there's multiple proxies. But I do want to talk about ice cores. Now, this is a really important proxy, not just for temperature, but also for carbon dioxide concentrations. Now, thin cores of ice, thousands of meters deep, have been drilled into the ice sheets of Greenland and Antarctica. Now, this picture here is a climatologist colleague of both Krista's and mine. His name's Eric Ostenberg from Dartmouth. And this is a picture of him at his research station on the Greenland ice sheet. Now, his ice cores, once taken, are transported from Greenland, okay, in what is it? Liquid nitrogen. So it's very, very cold, and they want to make sure that everything stays intact, okay? And so the glacier ice is put into containers at the station. It's loaded into a large plane that lands on the ice sheet, and then it lands in Logan Airport. Well, actually, it lands in at a military base first because it's a military plane, and then it goes to Logan, and then it's taken to his lab, which has a special refrigeration unit for later study. Now, glacier ice is formed as each year's snow is compacted under the weight of the snows of later years. And so light bands correspond to the relatively fresh snowfall. It's clean because it falls in the summer, when warmer conditions bring more moisture and precipitation to the Greenland ice sheet and the Antarctic ice sheet. Now, the dark bands mark the polar winter season, or the Antarctic winter season, when little new snow falls on these frigid deserts, and blowing snow is mixed with dust, carbon black, and other things that discolor the snow. Now, these layers are only millimeters to centimeters thick. Counting them, and basically looking at knowing that you go from white to black in a year, you can actually date what the date is along the whole length of the ice core. Now, crucially, the ice also encloses small bubbles of air that contain samples of the atmosphere. And from these, it is possible to measure directly the past concentration of atmospheric gases, including the major greenhouse gas, carbon dioxide, methane, and nitrous oxide. Now, scientists are also able to use the ratio of oxygen isotopes. That isotope is the same element, but with different atomic nucleus structure. And they can basically measure that ratio in the glacial ice as a proxy for air temperature above the glacier. Now, there was a recent event where the Earth's climate shifted from a 500-year warm period to a significant global cooling, and especially in the northern latitudes. Now, this is often referred to as the Little Ice Age. Now, the Norseman Eric the Red discovered and named Greenland around 980 AD. And at this time, the discovery was in the midst of a global warming period that ranged between approximately 800 and 1300 AD. Now, there are many reasons why the Greenland Norse did not flourish. By 1500, there were no Greenland Norse on Greenland. And many reasons, such as not adapting their food production practices to the realities of the environmental constraints of Greenland. They refused to use indigenous knowledge from the Inuits, who had been there for thousands of years. And their economy and social structure actually was maintained by trade and information with the European Norse in Norway and Denmark. Now, to this latter point, regarding the essential dependence of Greenland Norse on European economic support, such support required dangerous one-way trips between Greenland and Norway, which at a minimum took 2 weeks or more. Let me back up. But during the Little Ice Age, 2 things happen. One is the frequency and intensity of storms in the North Atlantic increased dramatically. And you can see the sailing vessels of the North. They were pretty skilled sailors, but they had very low gunwales, and it was easy to swamp these boats. But also, the one thing that happened is you started to see large ice flows, and as such, the Norse from Europe just ceased trade altogether. So this is a good example of how climate temperature created a stress or stressor on the Norse economic system to the point of a system shift, contributing to the eventual collapse of the Greenland North. And this was due to the lack of their community's resilience as a result of their failure to adapt to their new environment. Now, the IPCC, the UN, basically defines such a quick change in the climate that was seen like the Little Ice Age, where basically a climate dynamic shifts. It can be temperature, it can be precipitation, it can be heat. But basically, it crosses some kind of threshold and it triggers a rapid shift from one state to a new one. Okay, we call that a system bifurcation. And once they cross these thresholds, they do not go backwards. Now, we did talk about the Little Ice Age, but this is a record of climate variability going back 20,000 years. And before the Little Ice Age, there were two really significant climate shifts that we need to look at. The first is what we call the Younger Dryas. One sees a dramatic shift in the northern Atlantic temperatures at the end of this period, at the end of what's called the Younger Dryas. Based on proxies, global warming occurred over a period of only 50 or 60 years, with some of the studies projecting that it took a shorter amount of time. Now, after the Younger Dryas, there was another event. We call this the 8.2K event, or 8,200 years ago. And according to the available data, at the beginning of this climate period, okay, at the beginning of this cooling, temperatures shifted very rapidly, and the Greenland ice cores show a temperature drop around 3.3 degrees centigrade, or which is huge. And they said this change took place in less than 20 years. This cold period approximately lasted 150 years, and the warming was just as rapid, showing an increase over a period of 2 decades. So another definition that the United States Geological Survey came up is that abrupt climate change is a change in the climate that takes place over a few decades or less and persists for at least a few decades, and it will cause substantial disruptions to human and natural systems. Now let's talk about a current phenomena. This is a characterization of what is known as the Pacific Decadal Oscillation, or the PDO, which has two phases, a warm and a cool phase. The phases are determined by the temperature of the ocean's surface. The PDO's phases are influenced by direction of the winds in the North Pacific, if anybody's taken Earth systems. And as you can see, during a warm phase, the ocean responds to low atmospheric pressure over the Aleutian Islands, and it brings warm water to the Eastern Pacific and North American coast, and cool water to the Western Pacific. Because as warm water heats up, it expands, this leads to higher sea levels along the Northeast Pacific coast during this warm phase. Now, during the cool phase, the Eastern Pacific becomes cooler and the Western Pacific becomes warmer. And thus for us in the Northeast, it leads to a lower sea level during this period. Now, the PDO phases, the cool and warm, are generally longer term changes lasting 20 to 30 years before they change back. However, if you look at this graph, there is a higher frequency of variation within the longer PDO variation phase. So I'm going to ask anybody, and just pop in, well, why do you think this dynamic may be? Basically, this fluctuation that is much faster than the PDO, which crosses from cool to warm, cool to warm. See if anybody can guess what that dynamic is. So when you've talked about climate variability and trying to prove something some climate change is not attributed to human causes. This is one of the causes of climate variability they point to that are not generated by human causes. Does that help anybody? Okay. Well, if you listen to the news, you often hear about this on an ongoing basis. Now, these small variations are more well known as El Nino and La Nina phases. Okay. And these impact North America and Asia and have a variation of an average of 9 years. Okay, so they're much shorter, and that's the average variation. And so there's these up and downs that you see in the blue curve. And these yellow lines are just basically showing the trends of the PDO during the cool and warm phases. However, the hashed yellow line is a trend line of the increase in both the cooler temperatures as well as the warmer temperatures since the recording of the phenomenon started. So you can see, again, review, you have this, well, back, go back. You have this fluctuation of El Nino, La Nina, okay? And then you have this multi-decadal fluctuation of the PDO. And as you see over time, the cooler temperatures are getting warmer and the warmer temperatures are getting warmer. So what does this imply for you? What do you think about this once you see this variation and the increase in the trend of warmer temperatures, both cool season and warm season? Anybody?
So it looks like there's still variation no matter what, but the overall trend is increasing.
So what does
Temperature.
that imply, Jacqueline?
Global warming?
Not necessarily, okay, but yeah, I mean, this is a course in climate change. So good guess. And it basically implies that the trend that you're seeing, the upward trend that you're seeing, that there is another system that is or another system dynamic that's influencing what we're seeing that is not recorded here. Okay. And so we don't know what, right at this point at this slide, what it is attributed to, but it does make sense that because we're talking about temperature, that you could say that there's another system dynamic in the climate that is causing that increase, that we don't have any evidence of that except that you see the trend line going up. Does that make sense to everyone? Now, one possibility is that the larger system is shifting, being forced by what we call an unchecked change. Now, in system theory parlance, the phenomenon is known as a reinforcing or positive feedback loop. Now, if unchecked, it can cause an abrupt system shift. Okay, so that line, that trend line was showing us that there basically is some driver that is not being controlled, that is continually showing us an increase in both the warm highest warm temperatures and the cool highest warm temperatures. So we need to think about these feedbacks that we can't control or why they're not being controlled. Okay, and so let me look at now. One thing we see, okay, is that here we see a positive feedback of just carbon. Okay, and shows the speed of climate change. And basically, what this is showing is a shift of temperatures taken in ice cores at the September period and at the March period. And we're seeing that during March, we haven't seen a big fluctuation of percent difference in CO2. And if we look at the red, we see in September, if we looked at the Septembers of every of those bands that Eric Osterberg was taking, we see a dramatic change in September of CO2. And this indicates that something's happening on the planet in which in spring, CO2 is not as low as you see in March. And a lot of scientists have noticed this in carbon dioxide monitoring at Mauna Loa Observatory in Alaska, which has been measuring atmospheric CO2 since 1960, sees a variation every year between CO2. And so in the summer and early fall, depending on where you're measuring things, you will basically see an increase in CO2, decrease in CO2 because of all the vegetation growth that is on the planet, and that's every place on the planet, including the Amazon and the Congo rainforest, which are big players here. They basically consume the CO2, okay, for growth. However, in March, a lot of the biota is basically in senescence, and you don't see that. And so this up and down that you would see every year is called the lungs of the earth. And scientists view Brazil and the Congo as the key points of the lungs of the earth. Okay. Now, let me just go here. I'm looking for something. Sorry, I'm having a little technical difficulty here with my slideshow. Okay. Slideshow is frozen. Give me a sec. I'm going to stop it and start it again. Give me a sec. Sec. go back. Okay, I'm gonna share. Sorry about that. Welcome to my world. Okay,
If you're graphic heavy,
share. Okay, you should be seeing horses at the moment.
yeah, we see them.
Okay, hold on. One more time. So let me get back to unchecked change. Okay. That is basically what is being forced. What is the stressor in the system? In system parlance, I said basically this is a positive feedback. Now, Arctic sea ice is melting faster than expected, reducing the Earth's what we call albedo, or its reflectance, its ability to reflect sunlight instead of absorbing heat. That basically, because Arctic sea ice is melting, it's where it melts is no longer white, and then you got the ocean waters, which are dark, and dark material tends to absorb radiation and release it as infrared or radiation or heat. Okay. So what happens is, as you melt the Greenland Arctic ice cap on the ocean, and remember it's on the ocean, so it's just floating there. So if it melts, it doesn't change the volume of water in the ocean, but it does change the albedo. So as you reduce the albedo, you increase solar absorption, heat release, and thus you're warming the environment more, which then melts the Arctic ice more and creates more open water and thus more heat absorption and release. So this Arctic amplification is a positive feedback loop. Now, summer Arctic ice sea levels are at the lowest in recorded history. Some models now suggest that we could see ice-free Arctic summers, completely ice-free Arctic summers as early as the 2030s. And interesting enough, when I started in this field, in the late 1990s, the predictions of Arctic sea ice loss was going to be likely to occur by 2070 or later. So with current predictions based on new knowledge, okay, the recent climate model suggests that the free ice by 2030 is a full 30 or 40 years than previously projected. So something happened from the original, besides the granularity of the models, something happened that changed that projection, because sea ice loss is pretty straightforward for climate scientists to look at. But what's important here, which is much global in scale, is the loss of sea ice affects global atmospheric circulation. It has right now already been proven to disrupt the jet streams in the northern latitudes. And it's leading to more frequent and severe weather extremes in the mid-latitude regions, including bringing heat waves, droughts, and cold spells. And it shifts the Arctic temperatures, and the boundary between the very cold Arctic temperatures and the warmer lower latitude temperatures is starting to weaken. And so it is starting, as we're starting to see, very bizarre winter storms that may be rain followed by snow, followed by ice storms. And so this ice is triggering other positive feedback dynamics, okay, that may be much more consequential than just this feedback system. And because these other positive feedback dynamics may be occurring in concert with what we see in the Arctic ice, there's going to be a multitude of stressor chains on both natural ecosystems and human infrastructure and human societal institutions in the not too distant future. Now, let me say there are negative feedback loops, or what is considered regulating feedback, okay? These are the checks that basically create the checks and balances that keep a positive or reinforcing feedback from causing a system shift.
Michael, you're not sharing any slides, right? You didn't get them up.
No, I'm going
Okay.
to share it right now.
Okay, I just want to make sure we didn't miss it.
Okay. Okay, so I want to talk about checks and balances and controlling feedback loops. And this is so true if you're an ecologist, we see this all the time in ecosystem dynamics, where we see a beginning of a positive or reinforcing feedback beginning, and then a process occurs naturally that basically stops that spiral of positive feedback and corrects it. Okay, and so one of the positive feedbacks we have, probably the biggest positive feedback we have of carbon dioxide emissions increased by humans, is the ocean carbon cycle, which basically the ocean itself has the ability to absorb carbon, and actually analyses have looked at the dynamic and says probably 25 to 30% of human generated CO2 emissions, okay, are basically being subsumed or sequestered by the ocean. So I'm looking at the time. I know you want to have questions, so I'm going to stop there. So let me just review sort of the line, the line of thought for the presentation. One is that basically we can pretty accurately measure through proxies climate parameters such as CO2 and temperature with before instrumentation was invented. Secondly, that through that analysis of the ice cores, we can basically see the timing of when temperatures dropped and CO2 decreased, and temperatures went up and CO2 increased. They usually are linked hand in hand. And so we talked about a system, a stressor of temperature change during the medieval period, where basically you had a long warm spell, about 500 years, and then you had a cool spell, which between the warm spell and the cool spell was only half a century, and then it lasted 150 years. So, but as we saw, that basically just that short amount of time changed and had impacts on societal and economic systems and the survivability and resilience of humans during this time. The Little Ice Age was a very, very hard time, even in Europe, for people to survive. And you saw a big drop in population at the time. Then we talked about the Younger Dryas and also the 8.2K event. And what's interesting about this, the data is clearly showing that major global system shifts, at least for temperature, occurred in 2 decades or less, both cooling and warming. 2 decades. Okay, we're talking about major global shifts. Okay, and so the ramifications are quite large. And then we talked about the PDO as an example of, we're seeing some signatures or evidence of longer term shifts because of an increase in temperatures of both cool and warm phases. Yes, we can imply that that is climate change occurring. But the question is, at what rate is that change going to occur, and are we approaching a threshold where we're going to have a major system shift? And the things that increase the rate of change are positive feedback, such as Arctic ice. Okay, and the Arctic ice will have major impacts on global precipitation and temperature patterns. And you actually may see other positive feedback loops start to increase just because the Arctic ice feedback loop is increasing. That is why scientists are so strongly advocating that you keep the average global temperature below 2 degrees centigrade pre-1990. And if you don't, we're going to be crossing some of these positive feedback thresholds, and you can't go back. Once you've crossed them, you can't go back. Okay, so you have to adapt to the new normal, and you have to take steps very quickly to build resilience within your systems, both natural and human, in order for them to survive and not have the 6th great extinction on the planet. Okay, and I also wanted to point out there are negative feedback loops or controlling feedback loops that are in play that will help control more greenhouse gas emissions by humans. Obviously, the ocean has a limit, but for example, the rainforest and vegetation around the planet will do a lot, because 2 things it will do. One, it will sequester carbon into its tissue, and if you have trees that are living, for 200-300 years, that's not going into the atmosphere. Also, when vegetation dies, it decomposes and it goes into the soil, and carbon is sequestered in the soil. And unless the soil is disturbed, okay, it could be there, mineralization of soil that is going from organic soil to just minerals. And through that process, carbon dioxide is released in the soil. That can be a 50 to 100 year in the warmer climates, and it can be thousands of years in the colder climates. Okay, so vegetation and sequestration is a major negative feedback to human caused emissions. So not only preserving, but increasing the footprint of vegetation on the planet will help. So I'll stop there, okay, and stop the share and just turn it over to Krista.
Thanks, Michael. Sorry about your tech difficulties. But this would probably be a really good time for us to talk questions. And actually, at this point, I think I'm going to turn the recording off. Just because then we all feel more comfortable asking questions, no matter how they sound. So we can talk about this a little bit more. Hold on.